Well, it's an honor for me to be here. I offer my congratulations to the Berkeley community for your new center. It's an exciting group of people, concepts, and it'll be fun to see how it grows and changes the world. I also want to give my best regards to John Clark. In the 80s, I was reading your papers. As an atomic physicist, I had to do it under the covers at night with a flashlight. Weren't so well known, but it was a really spectacular and a great challenge and inspiration for my life to get to what we're trying to do now even. So I want to try to give kind of what the context of my talk is more broadly in some setting of the other talks today. It's a grand challenge to try to build exotic quantum systems, new quantum phases of matter, quantum computers. It's not a grand challenge like driving home from the Los Angeles airport to my home. That's a grand challenge. It took me 2.5 hours a few weeks ago in the rain, but it's not a challenge that you really want to deal with. It's just a mess. This is a challenge which for this community, your new community here and people around the world, is compulsory. It's compulsory. I don't really have a choice about getting from here to there. I don't know how I'm going to do it, but I have to do it. The excitement of the scientific frontiers, both theoretically, experimentally, technical requirements, new theoretical tools that are developed to even imagine how to get across and through this and find out what's hidden from us now. We know enough to believe that there really is a new scientific future, a revolution, this second quantum revolution. The journey certainly is exhilarating, amazing achievements, but also devastating defeats in trying to get from here to there. And I want to tell you about some aspects of both the achievements and defeats. My goal for a long time, 20 years, has been to learn how to build the right kind of quantum Lego blocks so I could assemble complicated quantum systems. Systems whose complexity very quickly exceeds our ability to characterize them, say, in terms of a density matrix. Systems with behaviors that are different than what we can realize in the laboratory. And importantly to me is photons, propagating photons to find new kinds of material systems. And when photons propagate, there are phenomena that you can measure, like in the quantum Hall effect, like a superconductor. Who had to tell Omnis that this was interesting? Did he have to go talk to a theorist about errors in his density matrix diagonalization? No, it was just slap in the face. So that's what I'm after. And I've come over my career, certainly for 25 years, to believe that we have to find a new way. If the physics of the way atoms and photons interact, we have to find a new way to do that. That's what I've been trying to do for a while. Seems like a good idea, and Mother Nature gives me a slap down. No, it's not. Try again. So what I've come upon in the end of my career is to try to integrate nanophotonics, a really powerful technical world for structuring dielectrics, nanophotonic waveguides, microwave, all about that. Different kinds now that are suited more to atomic physics, photonic crystals. In one dimension, this is a one-dimensional slot waveguide, but surrounded by a two-dimensional photonic crystal. This is a honeycomb lattice, which can be just in linear physics, linear optics, have interesting topological properties. But if we put atoms in these structures, they can have really, I think, not just better properties in terms of how coherent they are, but in fact, new qualitative phenomena. So the goal is to integrate atomic physics and nanophotonics. This is the cartoon. Nobody's reached that point yet. We're at onesie twosies, but I'll tell you our progress and why we should want to do this. This is not driving to LAX. This is driving to, I think, some really exciting new physics. So, to give you one idea, let's talk about cavity quantum electrodynamics. Cavity QED, a long history. I spent most of my life doing that. Dan has some part of his life in frustration working with me to try to get some things done, now spectacular in his own lab. Two mirrors and put atoms. Well, there are rates for the way atoms and photons interact, and there are errors associated with those rates. But Vladimir Vilitek and Misha Lukin and their colleagues at MIT and Harvard have come up with a spectacular advance in the quantitative characteristics that we would never access in the conventional settings of cavity QED. And that's to make a little cavity. This is a photonic crystal that chirps along and spacing changes, and you make a defect mode. There's an atom shown pictorially and a localized field. It looks just like a cavity. Outside there's not much, inside there's a lot, and you put the atom there. And with that, they've been able to project just what in conventional cavity QED is 2 orders of magnitude beyond what people have achieved. How many photons do you need to saturate an atom? 10 to the minus 7. So it implies really strong coherent coupling to the dissipative coupling, and goes beyond what I've projected in papers that we could do with conventional kinds of cavity QED systems. Well, what about cavity QED in an unconventional way, a new paradigm for cavity QED? Let's take an atom. We need an atom for cavity QED, and we need a cavity, but let's let the mirrors be the cavity. I'll show you in just a moment that atoms can be highly reflective in a one-dimensional waveguide. So if the atoms can be the mirrors, then we don't need that because the mirrors are already quantum mechanical. The atoms are free to move, and they're quantum mechanical. So now we have cavity QED where the mirrors themselves are quantized. That's an unconventional. It's smaller, sure. There are higher couplings than we could get in conventional optical physics, but there's qualitatively new kinds of physics. I'll talk about atoms the whole time, but I don't want to overlook the spectacular advances continuing in the quantum circuit QED kind of community recently by Andrew Hauck to make photonic crystals, modulated periodic structures will be really important in my talk I'll show in a moment, but to not place atoms near them in the microwave, but superconducting quantum bits. So the physics we need is really simple. Think of a waveguide, think of some kind of emitter. I'm going to use atoms for the whole talk. One atom near some waveguide, hundreds of nanometers. Light propagates in, some of it reflects, some of it transmits. If the coupling of the atoms of the waveguide is big enough, there's a little impedance mismatching. And so some light reflects, some transmits. And the whole story of the reflection and the transmission is set by this gamma 1D, the emission rate into the waveguide compared to the free space to everywhere else. And you can calculate, it's a simple calculation, this 1D, that's what's important, is given in units of the Einstein A coefficient and some other things, free space cross-section of an atom and the group velocity. So if this is the look-in Jackson, the unitary limited cross-section for an atom is just lambda squared. So we need an area of the mode that's propagating that's small compared to that to make this number big compared to just spontaneous decay. In a waveguide, the velocity is not the speed of light, but the relevant velocity is group velocity. And we'll look in just a moment, just to foreshadow, if we can structure the dispersion relation, we can find places where the group velocity goes to 0. That happens at the edge of a Brillouin zone sometimes. So we can make this potentially very large, this good coupling, so we can potentially make atoms be really single atoms important for propagating photons. How important? If you just think about an optical fiber and now pull the optical fiber so its diameter is small at 400 nanometers, then light propagates through, you can get about 5% absorption for one atom trapped in the way people have near the surface. If we structure the waveguide, so these are meant to be holes, so now there's a modulation in the dielectric constant in a way which I'll try to explain on the next few graphs, you can have one atom attenuate 99% of the light. Mostly it's not attenuated in this channel, it's reflected. So the atom reflects 99% of light, and that's close to what we'll be able to do in our experiments, I think, even this year. So you have to go inside. So this talk's going to be the technical problems of making really good dielectrics and really getting single atoms trapped very close inside the dielectrics. So the thing I'll talk about, just because we've worked on it quite a bit, and I think it's in optical physics anyway, the kind of state of the art, is some modulated variation in the dielectric constant, and we call it alligator waveguide. This is a piece of silicon nitride, index is 2, it's 200 nanometers thick, the lattice constant is 370 nanometers, and what we're going to do is trap an atom inside of her. And in this setting, this ratio that I just told you about in our experiment, we're working to do this right now, we've got this ratio to be 1, and we think we can get it to be 10, in which case this transmission is just the number I told you, just to give you some figure of merit. You can use that to do the strong coupling. The thing that was mentioned by Steve Garvin is, well, don't be ashamed, physicists, that we're engineering. Look, atoms in free space are God-given and great, but they're not good enough. We have to engineer the environment and the radiative processes of these atoms, and band structure lets us do this. So here's just a band diagram, frequency and dispersion. Imagine you have a wavelength you want to trap atoms and a wavelength you want to interrogate them. In free space, those two length scales are necessarily different. If you have band structure, the wavelengths can be the same. If you go near the band edge, the group velocity here goes to 0, and this coupling diverges in lowest order. So we can make much larger couplings of atoms into this one-dimensional or two-dimensional dielectric than we could ever in free space. If we don't stick with one atom but lots of atoms, then we can begin to do new kinds of quantum mini-body physics, and that's what I really want to tell you about. Atom-atom interactions mediated by photons, photon-photon interactions along this dielectric substrate of atoms, and new kinds of quantum mini-body physics. So in a simple dispersion relation, there are going to be two regimes. One is when the photons are free to propagate at the photons that the atoms interact with. That's a domain in the dispersive regime, so we have the electric field like that. One atom in the excited state emits into the waveguide, just as I explained. Another atom could emit that, photons send the photon back. Those processes are described both by a coherent spin flip from excited to ground state and ground to excited state, but also by a dissipative term in the waveguide, a collective dissipation for these 2 atoms, 3 atoms, 4 atoms. If we put a bunch of atoms in there, then it's not just one with the other, but it's all I and J communicating down the waveguide. A waveguide like this in the dispersive regime is essentially infinite one-dimensional couplings for the atoms. The bad news in this story is the atoms don't emit simply into the waveguide, but into free space and leaky modes of the dielectric. So the figure of merit is going to be how big can we make this coupling, gamma 1D. It's just the Weisskopf-Wigner radiation rate, but into this structured environment. This is into all other modes. If we put the atoms pi apart, this spatially dependent term goes away, and then we can look at what kind of physics happens when the atoms now collectively emit, essentially super radiant emission. And the kind of thing that happens in quantum information, you want to get some kind of quantum state from here to there. A pretty well-known example is cavity QED to map a photon of the excitation of an atom into the photon reversibly. You can do all of that along a bus like this. More importantly, if you have a bunch of atoms, it's possible to make arbitrary spin states of these atoms like this. So this atom in its ground or excited state is spin up or spin down. And in this paper, we showed how to make arbitrary spin states of 1, 2, 3, 4, 5 of this theoretically. And then importantly, I would like to not just have the spins in the atom, I want to map those spin states to propagating photons and do it in a reversible way. And so we know how to do that, and the community generally has looked at this kind of problem for quantum memories of what are the eras that come about. And in this setting, the eras can actually be pretty small. The eras go not as gamma prime over gamma 1d, the inverse of this figure of merit, but there's an n there. The atoms essentially act as one super radiator. And so the collective mode is the radiation rate is improved. Nonetheless, it's a 1 over n improvement. And what we'd like to do is better than that. We'd like to get an exponential win, which seems completely crazy. The kind of way you do that is error correcting codes, as we've heard about before for quantum memory. But a recent miracle from Derek Chang's group, which I could tell you more about later, is that it's possible to make quantum memories, at least theoretically, relative to the fundamental radiative rates, which have exponentially suppressed errors. And there's no error correcting code. It's almost as simple as I just showed you. You map atoms in and out, and there's really something special about these atoms coupled to 1D reservoirs, which I could explain later. Anyway, it's a hint that there's a possibility to do not just somewhat better, but really a giant leap in our ability to control coherent interactions of atoms and photons. A surprise happened in the last several years, led by Peter Lodel on the one hand and Arnold Rauschenbüttel on the other, chiral quantum optics. If you put an atom in next to a waveguide, as I've told you so far, and excite the atom, the emission goes out in both directions equally. Is it possible to put an atom in a nanophotonic structure and have the emission be handed? And the answer is yes, and that answer comes from something that everybody knows in nanophotonics, but these guys thought about as it applies to atomic physics. Light propagating this way in a nanofiber has circularly polarized light, but not perpendicular to K, but in the plane of K. So if you look at this, the light circulates like this, circularly polarized light, but it's along the axis of propagation. If the light's propagating the other way, the light circulates with a different handedness. So if you put an atom in here and define a quantization direction with a weak magnetic field, that single atom can change completely the propagation characteristic of the system. And these are measurements from an experiment that Rauschenbüttel did with atoms. Lodel has done experiments with quantum dots to show what's the probability if you put the atom over here that you'll emit just in one way. So this is the handedness. You put an excited atom trapped, here's a whole array of atoms, trapped, what's the likelihood that the emission goes to the right, say, with nothing to the left? That would give this value 1. And depending on what are called edge states in atomic physics, you can have very high directionality to the emission. Zoller and his colleagues have shown how using that you can engineer new quantum, not surprisingly, chiral quantum phases of atoms and photons in these directional waveguides. Okay, let's go back to this diagram. That's all in the dispersive regime. What if we look in the propagating bands? If the atomic frequency is inside the gap, that seems kind of stupid. You can't get light to and from the atom. In that case, the fields that are radiated are just exponentially attenuated in the simplest case. So an excited atom tries to radiate, if there were no external modes, this is just with respect to the waveguide, tries to radiate, but can't. Photon has nowhere to go, and there's a kind of skin depth, if you will, build-up of the radiation around the atom that was first described by Sadiev John and Gershon Krushitsky a long time ago. So that atom just sits there. It's a dressed atom with its photon. If there's another atom somewhere near, it would make its cloud. So this atom, if it were the one excited, if these tails overlap, could transfer its excitation to that atom. And that's a completely Hamiltonian reversible process. So if you think about excited in ground states, it's spin up, spin down. One atom goes down, the other one goes up. That's this term. And it's completely reversible, this term. What about the dissipation in the waveguide? Well, this is in a band gap. And that in an infinite waveguide gap, that emission is zero. In a finite length wave gap, it's exponentially suppressed. So it's the second time you've heard me say that. That's an error. This is an imaginary component of some Green's function in the response, and that component is exponentially suppressed compared to the standard rule of atomic physics, which is simply set by ratio of real imaginary parts of a Green's function set by Kramers-Kronig. Okay, if we put a lot of atoms in there, they all have their little localized modes. And again, this is the bad guy. The figure of merit is just what is this J, this is unit, what is this J compared to the spontaneous decay elsewhere. So controlling this is a big deal, but nanophotonics, as I'll mention in a moment, offers a way to do that. Okay, so all I've told you so far is inside the band gap, one can do spin-spin physics. This is just a spin flip. I'm describing in terms of ground and excited states. Of course, in atomic physics, we use the coherence of the hyperfine manifold in the atom. And that U is the spin-spin coefficient. And you can change its structure simply by moving yourself detuning. This exponential decay depends on the tuning of the atomic transition to the band edge. But there are more powerful ways to do it. And in a paper with my colleagues in Ignacio Sirac's group, we're able to show that you can make this arbitrary. Would you like to have this spin interact with another spin which is 10 lattice sites away in a translationally invariant way? Yes. Would you like to take a linear lattice and wrap it into a topology of a ring? Yes, you can do that. So you can make arbitrary interactions this way. On the other hand, for a slide I'll need in a moment, if you take the derivative of this thing, it's a force. So spin-spin interactions in this setting can naturally, hybridize is the wrong word, but interplay with the motion. And that's been worked out in really the first example by Derek Chang's group of a serious attempt to take, well, here are these toy Hamiltonians I'm telling you about that are natural for atoms in photonic crystals. Fine. Write down the spin Hamiltonian. So what? What kind of physics emerges? And this is the first example that I know of serious where people have tried to do that. So this is alligator waveguide in cartoon. These are atoms, ground excited state. No, they're the hyperfine states. Adiabacically eliminate the excited state, and they're trapped atoms. And Derek and his colleagues have calculated this phase diagram. The axis of the phase diagram is just the coherent coupling, hopping between sites. The hopping is mediated by photons. It's just this virtual photon in the cloud that can cause a spin flip and then go back. So that's the G. The delta is just the lattice spacing. So the atoms are trapped. What's the lattice spacing? And so that's the normalization here. H is an external magnetic field and applied to sigma z. So there's some phase diagram. This is a paramagnetic phase. This is a Neal phase. Those will be familiar to you. This is an interesting phase where the motion and the spin dimerize. So there is a triplet formed, an entangled state between neighboring spins, atoms, but it's only formed when this spin-spin interaction causes the atoms to move to a new position. So the motion and the spin are hybridized, dimerized. This is a spin-motion fluid where there, if you want to hop from one motional level, you can't do that with hopping in a correlated way with spin change. So it's an interesting new phase in the sense of, wow, this stuff that a number of people in the community have been trying to calculate theoretically, what kind of Hamiltonians might arise really do have consequence and, that could give rise to interesting physics. The other thing is not atom-atom, but these spins, imagine that spin dimerized phase I was talking about, what would happen if photons propagated along it? Well, here's a simple calculation by Derek Chang's group and another of Gershon-Kuraszewski's group. These are two photons. They're placed in a photonic crystal, and they're going to propagate. And the photonic crystal is arranged so that the spin-spin interaction has some range. And in particular, spin, this goes down, this goes up. The spin-spin interaction can give rise to an energy shift. And that energy shift gives rise to, if you move the resonance frequency, it changes the dielectric constant, give rise to, in this case, bound photons. You can watch this relative coordinate oscillate as the two photons, polaritons, propagate through the system. Nobody knows how to do this yet, but that's the theoretical community. That was 2. What about 3, 4, 5, 6? Can you do it in 2 dimensions? Can you make molecules in 2-dimensional photonic crystals like a benzene ring of photons? Just some comment about the reality of what we can do in the lab. This is the parts of a photonic crystal made by my group. This is what we call this alligator photonic crystal. Here it is. It took a few years to learn how to build these. You've got to get light through a fiber in, impedance match nicely, then into the photonic crystal and out. And we know how to do that. Here are the SEMs of those various components. This is what our chip looks like. This is what the alligator photonic crystal looks like. It's a piece of silicon nitride. This is a few hundred nanometers, 250 nanometers thick. It goes on and on and on and on. And it took us a long time to learn how to make it. So when you look at this SEM, you really don't see errors at the level of a couple of nanometers. So we want to learn how to put atoms near that. Near that, in a setting where the photonic crystal has been designed, this is the band structure of the photonic crystal for TE and TM modes. It's been designed so that that point at the band edge corresponds with the cesium resonance when it comes out of fab to about a part in 10 to the 3, absolute. And then we're able to tune it to about a part in 10 to the 5th. So we're able to take the atomic transition relative to the band structure. That's going to be fixed, but I'll draw it here as if we're tuning the atomic transition and look both in the dispersive band and then put the atomic transition in the band gap. And when you do that, here's the experiment. We trap atoms along the photonic crystal. This is what the trap site looks like. The atoms are trapped about 130 nanometers from the surface. The guided mode is coming out of the plane at you. You have to do Casimir-Poulter calculations for the surfaces. And we're near the band edge, going into the band edge, so the block mode that determines what gamma 1D look like is a cosine squared. Okay, so we send light in, light comes out, just do transport measurements, as any good condensed matter physicist would, and see what we see. And from those, we can infer the real and imaginary components of the response function. This is what in quantum optics would be called super-radiant emission. This is into the band gap. The emission is inhibited. From the line shapes, we can infer dipole-dipole interactions. How do the dipoles interact? Again, it's by photon-photon exchange. And inside the band gap, that photon-photon exchange comes without dissipation into the waveguide. It's exponentially suppressed. So let me just show you that. This is what you would get if you did the same experiment in a cavity QED setting. If these were just atoms trapped inside a cavity. This is what we infer from our measurements. And we tune from atomic transition over here to in here. And what we see in that case is the cavity QED goes like this. In this dispersive regime, they behave pretty much the same. Now the ratio, this is the ratio of coherent to incoherent evolution, that grows and grows and grows relative to cavity QED. It grows in cavity QED because that's just the ratio of the real and imaginary components of the susceptibility, if you want to say it that way. And that's been the shackles of atomic physics all my life. And now we have a new way out. That ratio grows exponentially. The ratio of coherent to incoherent grows exponentially as you go inside the band gap. So that's the alligator. These nanophotonics offers lots of opportunities for engineering of photonic crystals. This is the next one we're going to use. It's a slot waveguide designed in collaboration with the Oscar Painter's group and built by Su-Ping Yu, a really remarkable graduate student. And This is to get light into the central region. The central region is the photonic crystal here. It's a slot. This is vacuum. This is where we're going to trap the atoms. There's a triangular lattice on the outside, so we put atoms in there and try to study their interactions. And I'll tell you in just a minute, we think we can go yet an order of magnitude right away beyond where we are now, and I think 2 orders of magnitude in the next few years. This is all part of engineering this thing, so it works. This is a funny version of impedance matching to get light in and out with high efficiency. So if we put all that together, these are the graphs I just showed you. This is this J and gamma 1D for 3 atoms in the experiment. And if we did that experiment in that new structure, this is what those graphs would look like. So again, inside the band gap, the decay into the guided mode is exponentially suppressed. The dipole-dipole interactions, that's the J spin-spin term, is here at 10, more or less. That's 10 in units of 5 megahertz. So that's dipole-dipole interactions that run at 50 megahertz. So these questions of ultra-low temperature and small coupling coefficients, no, one of the goals of this research is to find a way to do this where the spin-spin physics, the atom-atom or photon-photon interactions have rates which are tens of megahertz. Okay, we've done all this in 2 dimensions. The theory of it worked out with Derek Chang's group. The band structure is a little more complicated, but you can find the right kind of things in photonic crystals. You can find ways to really trap atoms in a way that's as good as free space. We haven't demonstrated that yet, but we can calculate kind of all the imperfections we know, but we got to do it to make it for real. And then when they're trapped, there's another part of the band structure where we have these enhanced interactions near band edge. So it's possible to do all of these kind of things with the engineering these structures right. And what we've calculated theoretically and are trying to get to in the lab is this quantum magnetism in 2 dimensions, topological atom-photon matter, using techniques very much like Wolfgang's group has pioneered, Raman transitions between neighboring sites to give us arbitrary spin control. Photon-photon interactions, I already mentioned that. At some level, this lattice of interesting quantum phases, if we can make them of the atoms, give rise to a quantum dielectric for light, where the propagation properties, the band structure of that thing all depend on the photon number. So it really becomes quantum. We've made some of those. This is a square lattice. We learn how to efficiently couple in and out of 2-dimensional structures. And we've made, here's what we hope will be Haldane's honeycomb lattice when we get atoms trapped in it to do physics with that. So the kind of place we're going is, I think the old quantum optics wasn't up to the challenges of the new world of quantum information science. So we're trying to make these quantum dielectrics. These are cartoons of atoms trapped in a 2-dimensional photonic crystal. This lattice spacing can be anywhere from 50 nanometers to 500 nanometers. So it really is something that we're not bound by the free space wavelength. And I've told you kind of the motivation and the kind of what we're trying to do. Far from it, we, the whole community, is to really make interesting quantum phases of light and matter and functional quantum optical circuits that could do things that could be interesting for the things like quantum communication, quantum memories, quantum metrology. So with that, let me thank the young people and thank you for your attention.
Thank you. Jeff, are there any quick questions? Yes, Storm.
Yeah, how much of an effect does the actual dielectric matter have on the physics that you're studying here, as opposed to just with trapped atoms plus light fields?
Oh, well, if you forget about the atoms, when you go near the band edge, the group velocity goes to 0, right? In a regular thing like I showed you the alligator, it's pretty simple quadratic. And so how much enhancement we can get from going near this band edge. Enhancement in all the rates I told you, J, this gamma 1D, derived from the structure of the dielectric. So in the simple case of going near the band edge, you've got to get the modes right. You got to put an atom where the light's bright, right? So you have to learn how to do that. So you got to design them. But having done that, the density of states, if you want to say it that way, radiative states of the dielectric substrate, that's the whole story. If you would go away from this kind of paradigm of quadratic behavior near band edge, like in the slot waveguide, one can tailor the functional form of the modes that just, what would you like? Would you like it completely flat? We've made structures which have group index of 3,000. So that would be 500, well, that would be 100 times larger than anything we've been able to do so far. So the dielectric structure is really important to this because it's not free space. And so learning how one does that is really important. We think, though, that having said that, if you make the right kind of dielectric, like this hexagonal lattice, atoms inside of that can functionalize it to make it violate time reversal invariance and give rise to interesting quantum phases in say, quantum magnetism that you couldn't get otherwise. So the dielectrics are really important, but so are the atoms at the end of the day in functionalizing the dielectrics.